Ever been sitting on a bus that suddenly slams on the brakes? What happens to you? You lurch forward, right? Even though you weren't actively trying to move forward, your body seemed to want to keep going. Or think about pushing a heavy box across the floor. It takes effort to get it moving, and once it's moving, it seems to want to keep sliding. What's the underlying principle at play in both of these seemingly different scenarios? It's something so fundamental to how our universe works, a cornerstone of classical physics, and it was elegantly articulated centuries ago by one of history's greatest scientific minds, Sir Isaac Newton. We're constantly interacting with this principle, often without even realizing it. From the simple act of a ball rolling to a stop to the complex orbits of planets, it governs motion in ways that are both intuitive and surprisingly profound. It's the bedrock upon which much of our understanding of mechanics is built. So, what exactly is this fundamental idea? What did Newton discover that explains why you fly forward on a braking bus or why a rolling ball eventually stops? Before we dive into the specifics, let's take a step back and appreciate the world Newton was living in. Imagine a time before cars, airplanes, or even reliable electricity. Understanding motion was a puzzle that had occupied thinkers for millennia. Aristotle, the great Greek philosopher, had proposed that objects naturally come to rest and that a continuous force was needed to keep them moving. This idea held sway for nearly 2,000 years. It seemed to align with everyday experience. Push a cart, and it stops when you stop pushing. Throw a ball, and it eventually falls to the ground and stops rolling. But there were whispers of dissent, observations that didn't quite fit Aristotle's neat picture. Thinkers like Galileo Galilei, through ingenious experiments, legend has it, dropping objects from the Leaning Tower of Pisa, though the historicity is debated, began to challenge these long-held beliefs. Galileo, in particular, explored the concept of inertia, the idea that an object has a tendency to resist changes in its state of motion. He imagined a ball rolling on a perfectly frictionless surface. He reasoned that it would continue rolling indefinitely because there would be no force to stop it. Now, enter Isaac Newton in the 17th century. Building upon the work of Galileo and others, Newton synthesized these ideas into a comprehensive framework for understanding motion. In his groundbreaking work, Principia Mathematica, published in 1687, he laid out three fundamental laws of motion. And the very first of these laws, well, that's what we're here to unravel today. So, let's get to the heart of it. What exactly is Newton's first law of motion? It's often stated as, an object at rest stays at rest and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. That might sound a bit formal, so let's break it down piece by piece. The first part, an object at rest stays at rest unless acted upon by an unbalanced force, probably feels pretty intuitive. Think about a book sitting on a table. It's not going to suddenly leap up and start dancing around the room on its own, right? It will remain at rest unless some external force acts on it. Maybe you pick it up, or the table gets bumped. The key here is unbalanced force. If all the forces acting on the book are balanced, like gravity pulling it down and the table pushing it up with equal force, then there's no net force, and the book stays put. Now, the second part, an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force, might be a little less obvious in our everyday experience. Why? Because in our daily lives, there are always forces acting on moving objects. Think about that rolling ball from earlier. It doesn't keep rolling forever, it eventually slows down and stops. According to Newton's first law, this means there must be an unbalanced force acting on it. And indeed, there are. Friction between the ball and the ground, and air resistance, are both forces that oppose the motion of the ball, causing it to decelerate. Imagine, for a moment, a scenario where these forces were absent. Picture a puck sliding across perfectly smooth ice in a vacuum, no air. Once you give it a push, it would, in theory, continue sliding in a straight line at a constant speed forever. There would be no force to slow it down or change its direction. This is the essence of inertia, the tendency of an object to resist changes in its state of motion. Newton's first law is often referred to as the law of inertia. Inertia isn't a force itself, rather, it's a property of matter. The more massive an object is, the more inertia it has. Think about trying to push a small car versus trying to push a large truck. The truck has significantly more mass, and therefore, more inertia. It's much harder to get it moving, and once it's moving, it's much harder to stop. It resists changes to its state of motion more strongly. Let's revisit our initial examples with this new understanding. When the bus slams on its brakes, your body, which was in motion along with the bus, tends to continue moving forward due to its inertia. There's no direct force immediately acting on your body to stop it as quickly as the bus is stopping. That's why you lurch forward until another force, like the friction from your shoes on the floor or the seatbelt, acts to slow you down. Similarly, the heavy box requires a significant force to get it moving because of its inertia, its resistance to changing from a state of rest to a state of motion. Once you're pushing it and it's moving, it wants to keep moving due to that same inertia. You have to keep applying a force to overcome friction and other resistive forces to maintain its motion. When you stop pushing, these unbalanced forces eventually bring the box to a stop. Newton's first law might seem simple on the surface, but its implications are profound. It tells us that a force is required to change the motion of an object. If an object is at rest, a force is needed to start it moving. If an object is moving, a force is needed to speed it up, slow it down, or change its direction. In the absence of a net force, things just keep doing what they're already doing. This was a radical departure from Aristotle's view, which suggested that motion naturally decayed. Newton's law established that uniform motion in a straight line is just as natural a state as being at rest. It shifted the focus from why things move to why they change their motion. Force became the agent of change in motion, not the sustainer of motion. Think about the vastness of space. Planets orbit stars, seemingly effortlessly, for billions of years. Why don't they just stop? Newton's first law provides a crucial part of the answer. In the vacuum of space, there's very little friction or air resistance to slow them down. Once they are set in motion by gravity, another force, which we'll touch upon later, they continue moving in their orbits due to their inertia. It's the gravitational force between the planets and the star that constantly changes their direction, causing them to orbit instead of flying off in a straight line. With that said, thanks for watching and until next time.